9.3 begins our study of three-dimensional figures. We start with our prisms and cylinders. Before we get into prisms and cylinders, we have to talk about our general names for solids. Before we talk about prisms and cylinders, I have to talk about some key features of various solids. First of all, a solid. A solid is any three-dimensional closed figure. A polyhedron is a specific type of solid. It's going to be a solid with any polygon faces. So it could have parallelogram, trapezoid, triangles, squares, so forth and so on, various faces. To the right, we see an example of a polyhedron. Please note, this is a polyhedron. This is not a particular prism or cylinder in this picture. So keep that in mind. Even though it's right at the top of our prisms and cylinders notes, this is actually a pyramid. So once again, this is a polyhedron. In this case, specifically, a pyramid. Despite that it happens to fall at the beginning of our prism notes. Now, in any polyhedron, a face is going to be any of the two-dimensional sides of a polygon. So in this particular picture, our face would be the shaded front triangle. Any other of the triangles in that picture, as well as the square base. An edge is going to be the intersection of two faces. It's going to be a line segment. So our top left arrow is pointing to an edge, as well as the top right arrow. Last but not least, a vertex is the intersection of two or more edges. It's going to always be a point. So our bottom right arrow is pointing to a vertex. Okay, so let's actually get into prisms specifically. So down below at the top page, or the front page, we have various examples of prisms. A prism is going to be a three-dimensional shape which has two matching polygon faces that are directly parallel from each other or across from each other. So a cube is actually an example of a prism, where if you pick two of the opposite faces that happen to be congruent, so in this case squares, and they're directly across from each other, as well as connect it with some rectangle or parallelogram faces, this is going to be a prism. In gray, we have a triangular prism, where the two gray triangles are going to be our opposite parallel faces. In our next picture in blue, we have a hexagonal prism because we have two matching parallel hexagons and rectangles which connect them. And then we have a rectangular prism because our two matching parallel faces are the shapes of rectangles. Once again, with rectangles connecting those parallel faces. The two matching faces that are parallel to each other will be referred to as the bases. So I always say parallel faces are the bases. The faces that are not considered to be the base are considered lateral faces. Those lateral faces could be rectangles or they could be parallelograms if we have what is called an oblique prism, which is more or less just slanted. Here again we have two prisms. Both of these are hexagonal prisms. The reason why I'm showing you these pictures again is because I want to show you where the bases are. The bases are not always the top and bottom, as many students may believe. The bases are always the parallel matching faces. So identify your bases first by identifying the two faces that are directly across from each other and are congruent. So in the blue picture, our bases happen to be the front and the back, whereas in the picture on the lower right, our bases are the top and bottom. The picture on the right is actually what we call an oblique prism. It works the same as a regular rectangular prism. So just keep that in mind. It doesn't matter if it's oblique or slanted. So how do we calculate the volume of a prism? The volume of a prism is calculated by capital B times H. So what is capital B? Well, capital B in our volume formula represents the area of the base. And this is going to vary depending on what the shape of the base is. If your base is a rectangle, you're going to use your length times width formula to calculate the area of the base. If your base is a hexagon, you're going to use your regular polygon formula, the 1/2 ANS formula. So when you're calculating or finding capital B, you have to choose the appropriate area formula. Now keep in mind, I'm not giving you all of the area formulas again because you already have them in your 9.1 and 9.2 notes. So you should refer to those notes to find these formulas as needed. The H in your volume of the prism is the height of your prism. I refer to this as the length from base to base. In every one of your prisms, the first thing you want to do is identify what the bases are. Then after that, you can calculate the area separately, identify the height separately, and then last but not least, calculate your volume. So let's go ahead and do that in the following examples. Example 1 looks like we have a triangular prism because our matching faces happen to be triangles. So these are our bases right here. First thing I'm going to do is calculate the area of my base. Because the base is a triangle, the formula that I'm going to use is the 1/2 base times height, the area of a formula. As I had mentioned before, this formula will always change depending on what your figure is. In this case, I have a triangle, that's why I'm using 1/2 base times height. Now, the base and the height are just specifically for the triangle. So when you're calculating the area of your base, ignore the rest of the figure. Only focus on the base itself. So when I'm doing this portion, I'm pretty much ignoring everything but this green triangle in the front and just focusing on this. For this triangle, the base appears to be 8 and the height appears to be 5, so not much needs to be done to solve for these sides. And I'll go ahead and plug in 8 and 5 for my base and height. Crunching these numbers, it appears that my base area is 20. Okay, so next I'll identify the height, this time of the prism, not to be confused with the height of the triangle. So the height of the prism is going to be the length from triangle to triangle. So if you look in our picture, the 10 is actually giving us the distance between the two tips of the triangle. So that's going to be our height. So now we have our base area, we have our height, so we can find our volume using capital B times our height of our prism, or 20 times 10, giving us a final volume of 200. Now with volume is actually a three-dimensional measurement, so its units will also be three-dimensional. So our answer would be centimeters cubed. Final answer, 200 centimeters cubed. All right, so let's take a look at 2. And 2 is actually going to be our toughest problem from this entire set of notes. Here we have a rectangular prism because our matching faces are the hexagons on top and bottom. We're assuming that this is a regular hexagon because we haven't been told otherwise. So that means that if I were to lay this flat, it would indeed look like regular hexagons from the front and back. Okay, so let's go ahead and find the area for our figure. For our base, since it's a hexagon, we're going to use the hexagon area formula, 1/2 ANS. We don't know the apothem. We do know the number of sides. The number of sides happens to be 6. And we do know the side length. The side length is also 6. So we need to find the apothem. So to find the apothem, what I would actually suggest is drawing the base flat. It's very important that you draw the base flat as you would see it, because if you try to draw it in your three-dimensional figure, sides and lengths are skewed and they don't always look like what they actually are. So I'm going to go ahead and resketch my base hexagon. And again, I'm going to try to do this to the best of my ability here on this tablet. It's not always the easiest. All right, so there's my hexagon. And I'm going to go ahead and sketch in the apothem that I desire right here. And I know that the side is 6, so that means that half of the side is 3. So here's the triangle that I'm going to use to find my apothem. As we had mentioned in our regular hexagon notes, the triangle formed within a regular hexagon is a 30, 60, 90. So therefore, the relationship that holds will be short times radical 3 equals the long. And since the short in this triangle is 3, that would tell me that the apothem is just simply 3 radical 3. So now I know my N, S, and A, and I can find my base area. 1/2 of the apothem, 3 radical 3, times the number of sides, 6, times the side length, 6 as well. Okay, crunching these numbers, half of 6 is 3, 3 times 3 is 9, 9 times 6 is 54, and we have a radical 3 as well. So 54 radical 3 is our base area. But we're not done yet, that's just the base area. Next thing I would do, since I'm calculating the volume of a prism, is identify the height of the prism. The height of the prism is the length from hexagon to hexagon. So the length from the top to the bottom side in this case, or I should say face. It looks like our height, or the length from hexagon to hexagon, happens to be 10 again. Last but not least, I'll use my capital B times H formula and multiply my base area that I found times the height, giving me an exact answer of 540 radical 3. And of course, it's a volume, so we should have a unit, and it should be cubic units, so centimeters cubed. This is our exact volume. If you would like a decimal equivalent, you could put it into your calculator. And the decimal equivalent turns out to be, let's see here, 540 radical 3, so 3 times the square root times 540 would be 935.31. And that would be centimeters cubed. Just make sure I copy that down again, 935.31, yes, awesome. Okay, and there's your volume of a prism. So once again, for volume of a prism, you're going to identify the shape of your base, find the area of that particular base using the particular area formula given in 9.1 or 9.2, find the height of the prism, and then multiply those. Okay, so let's move on to cylinders. So cylinders are actually in the same section as prisms, even though they are not polyhedrons, because a circle is not considered a polygon. They are in the same section because they actually have the exact same formula, capital B times H. However, in a cylinder, your base will always be a circle. So you could replace the capital B with the area of a circle, pi r squared h. So believe it or not, these two formulas are the exact same formula. Just capital B is replaced with its specific base, pi r squared. So I typically just think of the volume of a cylinder as pi r squared h. If you think of them as the prism and cylinder as the same formula, you can just think of capital B times H, and that would eliminate one more formula to memorize. So this is what I'm going to really focus on. So I'm going to kind of ignore these and just focus on the formula of the pi r squared h. Okay. Something's not right here. Why isn't this working? Okay. All right, so let's move on to our examples. So example number 1, determine the volume for each solid. So I'm just going to go ahead and write down the formula for the volume of a cylinder, pi r squared h. I need the radius of the cylinder, so the radius would be from the center to the edge of the circle, which is actually going to be half of the given diameter, so 3, so our radius is 3. And our height is the length from circle to circle, so it looks like it's going to be 4. So plugging these values in, my volume will be pi times 3 squared times my h, 4. If I would like to keep the exact answer, I'm going to multiply everything but the pi. So 3 squared is 9. 9 times 4 gives me 36. And then tack the pi back on. So 36 pi, once again, units cubed, is my exact answer, or I could get the decimal equivalent by, once again, plugging this in my calculator. So 36 times pi gives me 113.10 if I round. So 113.10 centimeters cubed. So that was pretty easy when you follow the formula. Cylinders are actually relatively easy as long as you can identify the radius and the height. Okay, so once again we have another cylinder. This time the cylinder is tilted on its side and the bases happen to be the left and the right. But the process is still the same. We're still going to use that volume formula. Pi r squared h. The radius in this case is 3. And the height is actually going to be the horizontal distance from circle to circle, 8 in this case. So multiplying everything but the pi, 3 squared is 9. 9 times 8 gives me 72. So I have 72 pi, and tacking on my units, centimeters cubed, this is my exact answer. Or, once again, you can plug this into your calculator and get a decimal equivalent if you prefer that. I know your science teachers prefer the decimals, but math teachers tend to like the exact answers. And we have 226.19. And we have cubic centimeters as our unit once again. And there's our final answer. So as you can see, cylinders is obviously the easier of the two shapes to find the volume of.